Okay, picking up from where we left off with our second part of the study of the sun, we're going to look at the energy that the sun gives off. Okay, the energy from the sun is going to be fusion. Fusion is going to be the combining of nuclei of lighter elements into heavier elements. On Earth, we can't reproduce fusion because we can't get atoms dense enough or in a dense enough area and hot enough where they would strike each other and stick together because they have nowhere else to go. And that's what happens in the core of the sun. They literally have nowhere else to go, and when they collide with each other, they then stick together, and that's where we get fusion, or the combining of nuclei of lighter elements into heavier elements. With a lot of nuclear reactors in terms of energy reactors on Earth, we use fission, where we split atoms apart. So that's the difference between fission, where we split atoms apart, and fusion, what happens in the core of the sun. Okay, looking at our fusion equation, okay, when we're taking hydrogen and we're turning it into helium, essentially in the core of the sun, when we stick those atoms together, we have a little bit of leftover mass from adding together 4 hydrogen and making that into 1 helium, and that gives us that little bit of energy, light and heat, that's left over. So we start to look at the layers of the sun. Okay, we're going to start in the core. Okay, consisting mostly of hydrogen and helium ions in a plasma state, more than 100 times as dense as water. This is very, very dense and very, very hot. Hottest place in the solar system at around 15 million degrees Celsius. And that is, again, a measure of how energetic those particles are. They're moving around very, very fast. So when they collide at those extremely high speeds, they actually can stick together, and that's why we can have fusion happen in the core of the sun. Outside of that area, we get into the radioactive zone. With the radioactive zone, okay, again, it's a plasma state, kind of a transition place as we move out of the core and we start to work towards our convection zone with that. Getting temperatures again ranging from around 8 million degrees near the core, and as we move further out there, around 2 million degrees as we get closer to the convection zone. Moving on from there, we're going to have other areas of the sun's layers. Okay, outside of that radioactive zone, or the radio zone, we're going to have our convection zone. Convection, just like we talked about with heat transfer, is going to be rising and falling currents. There's going to be currents, almost like a boiling pot of water, within this layer of the sun, where it's going to carry plasma up to the surface of the sun. And when it reaches that surface of the sun, it's then going to radiate out into space as light and heat. So think of it almost like boiling water. As those bubbles come up to the surface, that's what's then going to give off the energy, and it's going to then travel from the sun to other parts of the solar system and then sink back down and create a little convection cell within the sun. Temperatures there raising to about 1.5 million degrees, and again that varies a little bit as heat is carried from inside then up to the surface. We get to the photosphere, and the temperature we're going to see does drop a lot as we get to that visible surface of the sun. We get to around 6,000 or so degrees Celsius there, and that's where we're also going to get granules. Granules, that's what's going to give the sun a lot of different character. Those are the bubbles that come up to the surface. They could be as big as the state of Texas, so they are very, very large. And like I said before, if we think of it as almost like a pot of boiling water with convection taking place and those bubbles coming up to the surface, and they come up, pop as a little granule, and that could last up to 20 minutes. And then they kind of cool and sink back down, get heated back up, and that cycle will continue on. Looking here at a diagram of the layers of the sun. Again, we have our core here in the center. Okay, and that's where our fusion is going to take place. Then we have our radiative zone outside of the core, and we see here they even put in our nice little convection cells as it gets into that convection zone, bringing the energy from the inner parts of the sun up to the surface of the sun, or what we call our photosphere of the sun. That's going to be our visible surface of the sun. And we can see as we look at the surface of the sun, we also have on here some sunspots. Okay, all of these little different granules, okay, on the surface of the sun. And we also start to look at the atmosphere of the sun, which we're going to talk about as well, which would be our chromosphere, which that's going to give us the reddish look that the sun has. And then we get into the corona. For our two layers of the sun's atmosphere. Okay, looking at these outer layers now, we have the chromosphere. Okay, the sun's inner layer of its atmosphere, which extends thousands of kilometers above the photosphere. And the temperatures there are actually going to start to go back up. Causes the hydrogen to emit a little bit of a reddish colored light as it starts to warm back up as we get off of the surface of the sun. We're also going to look for some of the other features of the sun, some solar prominences. These are going to be the dense clouds materials that are suspended above the surface of the sun by magnetic fields. So what I have here is a video showing an example of some of those solar prominences coming off, almost like a solar flare as it starts to shoot off of the surface of the sun. These are almost like magnetic field lines that get crossed, and the sun then ejects them out into space. Then we get into the corona. Okay, the thin outermost layer of the atmosphere, which is 1,000,000 times less bright than the photosphere. Okay, and temperatures actually increase, which is very, very odd as we get up into those higher layers of the sun's atmosphere. It gets back into the millions of degrees. We start to look at some of the features of the sun. We talked about sunspots, and I showed some examples of those. Okay, they can range in size and in how long they are on the sun for. Okay, they can be very, very large as well. They can go from anywhere from a few months to only lasting a few hours. We went outside and were actually able to view the sun. And we looked at some images from NASA's SOHO observatory. When we looked at some of the images of the sun when we went outside, unfortunately on the day we were looking, we weren't able to see any sunspots. And we looked at some of the images from NASA, and we were able to see what the sun looks like. And all these different pictures going across the top, they're looking at different temperatures, so they're using almost like thermal imaging to look at them, where we're looking at tens of thousands of degrees, then so maybe around 1,000,000 degrees or so, 1,500,000, and then finally to about 2,000,000 degrees. So they use that to kind of get a different look at different parts of the sun. Down here we're looking for sunspots, as we can see for the day that we're looking at today, April 30th. Not very, very active in terms of sunspots. And then we look at right here images for like chronomass ejections. And CMEs, harmful particles coming out of the sun, or ejections coming out of the sun. As we go back to our notes, we're going to finish off this section looking at the solar wind and magnetic storms. So the corona is going to give off a constant stream of electrically charged particles, and that's going to be called the solar wind. It's mostly made up of protons and electrons that are emitted from the sun. Okay, Okay, they fly at very, very high speeds at about 450 kilometers per second, reaching Earth in a few days. Not quite the speed of light, but still traveling very, very fast. Earth's magnetic field is going to deflect those harmful particles from hitting Earth's surface. And when they deflect those harmful particles from hitting Earth's surface, that's going to give us auroras. As those solar winds blow past Earth, some of those particles are going to interact with Earth's magnetic field and the upper atmosphere, causing auroras, which are displays of colorful lights appearing in the upper atmosphere. As we take a look here at some of those, what we call northern lights, aurora borealis, or in the southern hemisphere they have the southern lights, aurora australis. When those particles connect with the magnetic field, they also interact with the upper atmosphere and cause some of the gases in the upper atmosphere to glow, and depending on the gases that are there at the time, they will glow different colors. So we can see here some of the different colors that they can glow, and they make different shapes in the night sky. And that's again with the interaction of the solar wind and Earth's magnetic field. And that Earth's magnetic field is generated from the inner and outer core of Earth spinning inside the Earth, and it gives off that magnetic field. And Earth is very, very lucky that we have a strong magnetic field, stronger than an average planet our size, which gives us a little bit more protection from this solar wind. We look to a planet like Mars that does not have as strong of a magnetic field, and its atmosphere keeps getting stripped away by the solar wind because it doesn't have a strong enough magnetic field to protect itself from the sun and that harmful solar wind. That pretty much brings us to the end of our section here talking about the sun and what's going to be our quiz. If you have any questions, feel free to stop by in class and ask.